Welcome. We are going to do a quick explanation of the homework that we have due at problem set number 1. I'm hoping that some of my explanations for how to do some of these problems can be helpful as you explore some of these problems in astronomy. This is what you should see when you log into our Blackboard site, and we're going to go to problem set number 1. The first problem set, visual astronomy and calculations. This first question asks me to deal with large and small numbers. And we deal with large and small numbers by writing in something called scientific notation. Scientific notation just means that I'm going to be dealing with the size of the number, as well as the precise numbers that we use to describe approximately where on this thing we call a number line, the number lines. And we have names for big numbers and we have names for small numbers, and they're listed here for you to use. And we'll start off with the translation. The first thing we're doing here, for example, I'm asked to translate what is the distance to Jupiter if it's 780 million kilometers. So you may have to read a bit from your textbook and review maybe the videos that we have on scientific notation to answer this, but hopefully you can start to work on these. In this problem, you'll be asked to translate between the sizes of different numbers into scientific notation. And then eventually, you're going to be asked to do a division problem in scientific notation. So you should review how that works. The reason that we're going to be using this is because this is how we're going to talk about big and small numbers, and we really don't have any other way. So this is just to get you used to that and working on it. Question number 2 asks you to deal with the scale of light units. That is the distance that light travels in a given amount of time. A lot of people get confused by this. They hear something like a light year, and they think that we're talking about a length of time, maybe a year. But that's not what we're talking about at all. A light unit instead is a unit of distance. It's telling me how far away something might be. And the way I would figure out how far away it was would be by taking how fast light travels and figuring out how far it had traveled in a certain amount of time. There's a simple formula that explains how that works. It's that distance is equal to a speed times a time. The speed in this case is the speed of light, and the time is whatever time you are given in that light unit, whether it's light years, light minutes, light seconds, and so forth. You can see some examples of these down here, how long it takes light to get to various places, like the moon, the sun, Alpha Centauri, and so forth. If you wanted to convert these numbers into light units, you could say that they were 1.3 light seconds away from the moon, or 8.3 light minutes away from the sun. In this problem, you're going to be matching, trying to figure out the light unit compared to the closest distance that's on that list. In question number 3, you're going to be using a simulation to try to look at the different scales of objects. You start off at a scale of 10 to the 0. And you can go up to very large things, and you can go down to very small things. And as you explore these different things, the goal is to find things listed on here that you can find the scale. So I actually did one here, a grain of rice. I found that the grain of rice was at about 10 to the minus 2. Let's check and see if I was correct here. So I'm headed towards 10 to the minus 2 here. And as I get closer and closer, you might be able to see that a grain of rice is coming into view. And there it is. Right at about 10 to the minus 2, I see that grain of rice. In order to do this problem, you have to choose an integer, 1, 2, 3, or 4, -1, -2, -3, and so forth, as your answer. No fractions or decimals allowed. Question number 4 asks you to convert from cosmic time into something that's more humanly relatable. And there's a whole explanation for how to do this here. It's essentially a division problem. And I actually did this for my own age. I am 40 years old, but in cosmic calendar time, it turns out I'm about 0.09 cosmic calendar seconds. And I did this by using the calculation that you see here, that 1 second of cosmic calendar time is 438 years of real time. And you can do that for your own age as well. Beneath, I have a number of different events that happened in the past, and I need to see how far off in cosmic calendar time, whether it's a few seconds, minutes, hours, days, weeks, months, years, whatever it is, I have to figure out how much of that time has passed since that event occurred, imagining that the entire universe's history was distilled into 1 year. Question number 5 asks me to think a bit about measuring the sun above the horizon and the North Star above the horizon. Now, if you're going to do this one, it might help to read a little bit of section 2.1 in your textbook, but let me draw a little picture for you to think about this. We're going to imagine standing on the Earth. This is my crude drawing of the Earth. And if I was standing at the North Pole right here, I would see the North Star right over my head. So this is me drawing Polaris, the North Star. It wouldn't matter what time of day I was looking. That's where that North Star would be. We call that an altitude of 90 degrees. If I see something that's right above my head, it's at an altitude of 90 degrees. What if I was standing at the equator instead? This is the North Pole here, but say I stood at the equator. Obviously, this is not the scale. If I stood at the equator, I would actually see the North Star at the horizon, which is at 0 degrees in altitude. You can imagine looking out over the horizon, and I would be able to see the North Star there, not to scale. So you have to imagine the North Star being very, very far away compared to this. It would look like it was basically at the horizon. So if I figured out that the North Star was at the horizon, I would say its altitude was at 0 degrees at the equator. And I would say that it was at 90 degrees at the North Pole. Now, the latitude of the equator is 0 degrees. This is the latitude of the equator. And the latitude at the North Pole is 90 degrees north. What if you were in between? Well, this is for you to figure out. If you're in between, where would you see the North Star? According to your latitude, what would you see its altitude to be? There's a very simple relationship. Another thing to understand is that the North Star is right above the axis of rotation for our planet Earth. So our planet Earth is rotating around this axis of rotation, and the North Star is directly above that. That means that over the course of the night, the North Star is the only star that doesn't change its position. That's a big hint for another question here. But there, of course, are other stars that do change their position. Today happens to be the equinox, which means that we had 12 hours of daylight and 12 hours of darkness. That 12 hours of daylight and 12 hours of darkness is due to the fact that the sun, only on this day and then another day in March, is directly overhead at the equator. So if I was going to put the position for the sun, maybe I'll put the sun over here. This is where the sun would be today, directly overhead at the equator. Here's my sun. So if you stood at the equator today, you would see the altitude of the sun as being 90 degrees. The declination of the sun is where it is located in the celestial sphere. In this case, it is located at exactly 0 degrees. So today, the declination of the sun is 0 degrees. I have a question here that says the sun's declination is at 20.5 degrees. Well, if it's at 20.5 degrees, this would not be the equinox, this would be closer to sometime near the solstice. This would be sometime either in summer or late spring, where the sun would be as far north or very close to as far north as it gets. It gets to be about 22.5 degrees north. 20.5 degrees is pretty far north. Now think about somebody standing somewhere else on the planet other than the equator or the North Pole. How would you figure out how far up the sun would get over the course of the day? Well, let's think about just for the equinox. If I was standing, let's say, halfway up this planet of ours, that's approximately where we are when we're in New York, standing right about here. I'm definitely not going to see the sun directly overhead like they do at the equator, but I'm also not going to see it at the horizon like they do at the North Pole. I'm going to see it halfway up the sky. I'm going to see it at about 45 degrees. If the sun's declination was somehow different, maybe it was further north, then at noon, I would see it a little bit further up the sky than 45 degrees. How much further? Well, the amount further that I would see it would be whatever I would see the sun at with my observation at the equinox, plus whatever declination the sun happened to be. In this case, it's a positive declination. It's above the celestial equator. And so I should see the sun at a slightly higher altitude than I do at the equinox. If it had been negative, I would see it at a slightly lower altitude than at the equinox. This requires you to think carefully and try to understand what is going on in the sky and how we measure these angles in the sky. This section 2.1 can be very helpful. Also, section 4 has a lot to say about this, or chapter 4 has a lot. Going to move on to question number 6. Question number 6 is also relevant to today. The Earth's axis tilts at 23.5 degrees away from perpendicular in the plane of the ecliptic as it orbits around the sun. What we're going to do in this scenario is we're going to change that tilt. We're going to either make it more or less. And as we change the tilt, the seasons are going to modify. We're going to see different explanations for how much or how little sun we're getting, either directly or indirectly. I encourage you to go through and really digest what it means for the seasons to exist here on our planet. But in this situation, I've got a new axial tilt. And what I have to do is I have to think about whether this axial tilt is going to make the seasons more extreme or less extreme. Imagine that I had no axial tilt. If I had no axial tilt, then the seasons would end up being basically non-existent because the axial tilt is what causes the seasons. What if I had a 90-degree tilt? What if it was tilted exactly on its side? Then I'd have the most extreme seasons I could imagine, where half the world would be facing the sun for half the year, the other half would not. This would be like the worst orientation of winter and summer you could possibly imagine. So that should give you some sense for how to start proceeding in this question. As you go on, you're going to have to think a little bit about where different things happen on our planet according to this tilt. We have different parts of our planet. We have the tropics, we have the polar regions, and we have the temperate zones on our planet. The polar regions are defined as those places on the planet where either you can see the sun for 24 hours, or you end up in the wintertime with at least 24 hours of darkness. That's the Arctic Circle, and it's related to the axial tilt of our Earth. It's 23.5 degrees away, which is approximately the axial tilt of our Earth, 23.5 degrees. We also have an area called the tropics. This is an area where if you lived in that part of the world, at least one day of the year, you could guarantee that the sun would be directly overhead at noon. That's where the sun is most direct. And it goes between the latitude, which is the axial tilt of the Earth in the north, all the way down to the latitude, which is the axial tilt in the south, 23.5 degrees in the north, 23.5 degrees in the south. Those are the definitions of the tropics. Those are the definitions of the polar regions. If the axial tilt changed, what you can have happen is those tropics and those polar regions can get smaller or bigger, depending on whether the axial tilt is bigger or smaller. There are even situations where you can end up with parts of the polar regions and the tropics coinciding with each other. Really, really interesting stuff. You are going to be tasked with trying to make sure that you can figure out where these different regions are in this weird situation where we change the axial tilt of the Earth. And as you do that, that's going to help you understand, I hope, how the seasons are related to positions on our planet. So this is what your problem will be for question 6. The remainder of these questions will be a set of questions that are related to chapters 1, 2, and 4 in your text. There'll be multiple choice questions, and they'll be different for every person in the class. If you can't figure out the answer to a question, the thing to do is to check the text, approximately the part of the text that is discussing these sorts of things. So look for these ideas and matters as you go through and do these questions. 14 total questions. Hopefully that works out. All right, so that's our exploration of problem set 1. It's just a brief and perhaps not complete, but at least it gives you a start. If you have additional questions on any of these things, please contact me and let me know. But we'll start with this. The other thing I wanted to mention is that you are going to have more assignments coming due. And one of the assignments you have coming due is a discussion board post. Let me look and see if I can share with you that discussion board post to show you how it works. What I need to do here is create a thread that uses this website to look at the sky on my birthday. So this is what the sky looks like right now. As I look up at the sky, I can see all kinds of things: stars, planets, deep sky objects, even the International Space Station. And at the bottom, we can see some different icons that you may need to use. I can turn on something called night mode, which makes everything red, not very useful unless you're going out to look. I can turn on the grid, and I could see things like the declination and the right ascension of the sky, which is useful if you're trying to do some of the problems that we were talking about on the homework. I could also look at the grid that shows me what the altitude, in other words, how high or low something is in the sky, and the azimuth, how far east or west things are in the sky. Also very useful for some of our problems. And finally, I can do things like turn on and off the landscape. So let me see if I can do that here. That's the landscape on and off. I can turn on and off the atmosphere, usually a bit more useful during the daytime when it's sunny out. And I can even turn on constellations and off constellations. Those are all various things that you might find useful. When you do this problem, you want to set the date to your birthday, and you can set the time to whatever you'd like. As you set it to your birthday, take a look and see what the sky looked like and try to answer those questions. Then go through and see what other people did and see if you can help them out and see what the sky looked like on their birthday as well. So that's that. This is what we have. I hope you enjoy going through this work. And if you have any questions, please contact me. Have a great day.